This video is about group homomorphisms. Sometimes we can come across two groups that appear different superficially, but which really share all of the same essential features. To give an example of that, let's consider this matrix group G that has upper triangular matrices with ones on the main diagonal and some integer in the upper right entry. So the operation in this group is going to be matrix multiplication. So now if we just combine a couple of elements in this group, say 1a, 0, 1, and 1b, 0, 1, and we perform our little matrix multiplication here, we'll find that what we wind up with is this matrix, again with ones on the diagonal, but this time in the upper right we have an a plus b. And so what we see is that this group is really behaving like the group of integers. When we combine two elements in this group, essentially what we're doing is taking the upper right entries and adding them just like we would in the integers. So this group G, it seems to us, is essentially just the integers under addition. And in fact, if we wanted to make some sort of formal correspondence between these two groups, we could define a function that assigns an integer a to the corresponding 2 by 2 matrix in G that has a as the upper right entry. On the previous slide, we had a natural correspondence, f, from the group of integers to this group of upper triangular matrices given by this. So f takes an integer a and sends it to this special upper triangular matrix that has ones on the main diagonal and an a in the upper right entry. So in what sense is this correspondence really natural? Well, the first thing to notice is that f is a bijection. That is, it sends the integers on to G in a one-to-one fashion. And then the other thing to notice is that this function, this correspondence, preserves the operation. That is, if you take f of a sum of integers, that's the same as multiplying the individual images inside the group G. So this sum here is happening within the group Z, and this multiplication here is happening within the group G. To see how that happens, well, let's just see if we take f of a plus b. Well, that gives us this upper triangular matrix. And we saw on the previous slide that that can be written as the product of these two individual matrices. But each of those are the image of something in f, namely it's f of a times f of b. So this relationship here does indeed pan out for this function. Okay, now this property of preserving the operation, what that means is that if that's in place and the function is a bijection, then any computation that you want to do in the integers, you can also do in this group G and vice versa. So to see a little bit about how that works, let's compute the sum 2 plus 3 in the integers in sort of the following roundabout way. So what we're going to do is we're going to make a computation in the group G and then pull it back into the integers and see that we get the right thing. So first we're going to take f of 2 and f of 3, because after all, we are interested in what happens with 2 and 3. And we're going to combine them together. We're going to make the computation within the group capital G. And that's going to give us this matrix product. Which yields this, and hence this. Now we know from up top that this function preserves the operation, and so really this thing is not only f of 2 times f of 3, it's f of 2 plus 3. And therefore, if I want to compute 2 plus 3 in the integers, how do I get that? Well, f is a bijection, and so it has an inverse function. So that means I can apply the inverse of f to f of 2 plus 3, which means I can apply the inverse function to this matrix 1, 0, 5, 1. And when I do that, I wind up with 5. Okay, so I get it. This seems like the world's most roundabout way possible to compute the sum 2 plus 3 and obtain 5. But the point is that we're able to make this computation in this other setting. Now, in this particular example, we probably wouldn't have any really great reason to compute 2 plus 3 in some other setting, but sometimes there is a good reason for doing this. The previous example leads to an important definition. We let G and K be groups. A bijection from G to K satisfying this property, f of A times B equals f of A times f of B, is what's called an isomorphism. And the groups, G and K, are said to be isomorphic. Now, it's important to understand where these computations are happening. So, for instance, the product A times B, that's happening within the group G, whereas f of B times f of A, f of A times f of B, that's happening in the group K. So the thing to be thinking about here is that if two groups G and K are isomorphic, then they are in all essential ways the same group. That is, if one is abelian, then the other is abelian. If one has an element of order 2, then so does the other. The only differences between these groups are superficial differences, differences of labels, for instance. But all of the intrinsic properties that G has will also be possessed by K, and vice versa. Our next example involves a group that you might recall with fondness from the beginning of the course. We have this group G that consists actually of the positive real numbers, except for 1. And the operation that we put on this set is A star B equaling A to the log base 10 of B. Now, we saw much earlier in the course that this actually is a binary operation on this set, and in fact, it's a group. Now, this looks superficially like an unfamiliar object to us. However, it turns out that this set with this group operation is just a disguised version of the non-zero real numbers under ordinary multiplication. So we're going to show that this group G, that we know and love from earlier in the course, is isomorphic to this group of non-zero real numbers under ordinary multiplication. Now, to do that, we need an isomorphism. That is, we need a function from one group to the other. And we're going to define our function from the non-zero real numbers to our group G by taking a non-zero real number x and sending it to 10 to the x. Now, it turns out this is a bijection from the non-zero real numbers on to G. And maybe, we're not going to prove that rigorously, but maybe a picture would help. So if we graph y equals 10 to the x, well, it looks something like this. And we can see, using the horizontal line test, that this is a one-to-one function. And you can also see that the range of this function is going to be all of the positive real numbers. But because we're not including 0 in the domain, we don't get 1 in the range of this function. Okay, so this function is bijection. But now we need to show that it preserves the operation. That is, we need to show that f of a times b here is equal to f of a times f of b, where the operation over here in our group G. Okay, well, let's start our chain of equations here. So f of a times b, well, that's 10 to the a times b. And then using a law of exponents, that's 10 to the a raised to the b. But we can write b creatively as the log of 10 to the b. But 10 to the b is just f of b, and 10 to the a is f of a. So this is f of a raised to the log of f of b. But that describes the operation over in G, namely that's f of a star f of b. And therefore, this function preserves the operation, and it's a bijection. Therefore, it's an isomorphism. Not all functions between groups that preserve the operation need to be bijections. So if you have a function from one group to another that preserves the operation, without any sort of mention about whether it's one-to-one or on-to or anything like that, then that function is what's known as a homomorphism. So there are all kinds of examples of homomorphisms. The first example, in our first bullet, is what's called the trivial homomorphism. And what it does is it just sends everything in the group G to the identity element in K. Now, it might be a good idea for you to perhaps pause the video and check to see whether that function is indeed a homomorphism. So another classic example is the function that takes the additive group of integers to the integers modulo n by just taking some integer and reducing it mod n. So this homomorphism is a surjection, that is, it's onto, and you can use it to define an isomorphism from the quotient group Z mod the cyclic group generated by n to Z sub n. So here in the future, perhaps in the next section, we're going to see that homomorphisms that are surjections, that is, onto homomorphisms like this one, can be used to create related isomorphisms involving a quotient group. Okay, and we have another example. Here we can have a homomorphism from the cyclic group Z3 into the symmetric group S3 that just sends a number n to this 3 cycle raised to the nth power in S3. So the important thing about this example is that this homomorphism is 1-to-1. And that means that the group S3 is going to be isomorphic to its image inside of S3. And in fact, we're going to see a little bit later, there's this very big theorem in group theory called Cayley's theorem, which says that in fact, every finite group can be regarded in this way as being a subgroup of some symmetric group. Now, there are a lot more examples of homomorphisms in the reading, and I encourage you to look at those examples. In this section of the book, there are a great many theorems given about homomorphisms and isomorphisms. Here, over the next several slides, we're going to review some of these theorems and prove a few of them as well. So the first group of theorems that I want to show you has to do with compositions of homomorphisms. So we're going to let G, H, and K be groups, and we're going to let phi from G to H be a homomorphism, and psi from H to K also be a homomorphism. Then 3 things are true. The first is that if you compose these 2 homomorphisms, you get a third function from G to K, which is again a homomorphism. Second, if the 2 homomorphisms are actually isomorphisms, then the composition, in addition to being a homomorphism, will also be an isomorphism. And then finally, if you take any isomorphism, because it's a bijection, you'll be able to form the inverse function. The inverse function is also guaranteed to be an isomorphism. Now here at the bottom of the slide, we have a proof of one part of this theorem. In fact, we're just going to prove part C, right? So we start with an isomorphism from G to H, and we want to show that phi inverse is also an isomorphism. So the first thing you need to do is show that phi inverse is 1-to-1 and onto, and it has those properties because phi is also 1-to-1 and onto. So all we need to do now is show that phi inverse preserves the operation. So we start with 2 elements, H1 and H2, in H. Remember, by the way, that phi inverse sends H to G. So we start with 2 things, H1, H2 in H. And because phi is onto, there are elements G1 and G2 in G, with phi of G1 equaling H1 and phi of G2 equaling H2. So H1 times H2 is this product, phi of G1 times phi of G2. But because phi preserves the operations, because it's an isomorphism, we know that that's equal to phi of G1 times G2. So now if you apply phi inverse to the product, H1, H2, well, that's phi inverse of phi of G1, G2, which is just G1, G2. But G1 is phi inverse of H1, and G2 is phi inverse of H2. And so what has happened here, we've shown that phi1 inverse of the product H1, H2 is phi inverse of H1 times phi inverse of H2, which is what we needed to show. So phi inverse is an isomorphism. The next set of theorems have to do with commutativity. So we start with 2 groups, G and H, and a homomorphism from G to H. First part of the theorem says if H is abelian and phi is 1-to-1, then G must also be abelian. The second part of the theorem says if G is abelian and phi is onto, then H is abelian. And then part C is not a surprise to us. It says if phi is an isomorphism, then G is abelian if and only if H is abelian. And this harkens back to an earlier slide where we were talking about the definition of isomorphism. And if you have two isomorphic groups, then they must be intrinsically the same, meaning that any property that G possesses, H will possess, and vice versa. So we would expect that if G is abelian, then H is abelian, and vice versa, in the case that this phi is an isomorphism. Okay, the proof that we give on the slide is for part A. So we're assuming that the group H is abelian and that phi is 1-to-1. And we're going to show that G is abelian. So we start with two elements in G. And I want to show that the order of multiplication for those two elements does not matter. So let's apply phi to the product G1, G2. That gives me, because phi preserves the operation, phi of G1 times phi of G2. But phi of G1 and phi of G2 lie within the group H. So this is an element of H, this is an element of H. And because H is abelian, we know that we can reverse the order without affecting equality. But now phi, again, remember, preserves the operation. So this is phi of G2 times G1. So what do we have? Well, we have phi of G1, G2 equals phi of G2, G1. But phi is 1-to-1, and that means that G1, G2 must be G2, G1, and therefore G, the group capital G, is abelian. The next set of theorems have to do with powers of elements and orders of elements. So we let G and H again be groups, and we have a group homomorphism, phi, from G to H. And we'll let n be an integer. So there are four parts to this theorem. The first is that if you want to compute phi of x to the n, then that's the same as computing phi of x and raising it to the nth power over in the group H. Second, if you apply phi to the identity in G, the only possible output is the identity in H. Third, if the order of an element x in G is equal to n, then the order of phi of x over in H must divide n. And in fact, if, part D says if phi is an isomorphism, then the order of x and the order of phi of x are actually going to be equal for every x in G. Okay, among these four parts, we're going to prove part C. So part C tells us something about the order of phi of x. Well, what are we going to do? Let's take phi of x and raise it to the nth power and see what happens. So phi of x to the nth, that's phi of x times phi of x, and so on, n times. But remember that phi preserves the operation, and so that means that that's just phi of x times x times x, and so on, n times, where this is all happening in G, right? So this is phi of x to the nth. But remember, that n is the order of x, and therefore x to the n is the identity. So we're taking phi of the identity, but then part B of the theorem says that you just wind up with the identity in H. And so what have we learned? Well, we've learned if we take phi of x to the nth power, you get the identity. And if you remember back in section 4 where we learned about orders of elements, theorem 4.4 then would tell us that the order of phi of x must divide n. Our next collection of theorems deal with cyclic groups. In essence, we see that there are only two types of cyclic groups. If you have a finite cyclic group, then that group is isomorphic to some group of modular integers. If the cyclic group is infinite, then it's isomorphic to the group of integers. Now this symbol here, which I may not have introduced yet, indicates that the two groups are isomorphic. So we begin by looking at part A as a proof, and there's some discussion of part B a little bit later in the slide. So for part A, we're starting with a finite cyclic group, which is generated by an element little g. And because the order of the group is n, we know that the order of this element little g is n, and therefore the group elements can be listed just as powers of this little g. It's going to be e and g squared up through g to the n minus 1. And after that, we just repeat group elements again. So we want to show that this group is isomorphic to z sub n. And to do that, we need a function to serve as an isomorphism. And our function will have domain z sub n. So it's going to carry an element j in z sub n to this generator, little g, raised to the jth power. This function's a bijection, and to show it's an isomorphism, we need to show that it preserves the operation. So we apply phi to this sum, j plus k, where the circle plus indicates that we're computing the sum modulo n. And by definition of phi, that's g raised to the j plus k power, where again the addition is modulo n. And in fact, we see that that is equal to g to the j plus k, where the addition is ordinary addition. And then we can use laws of exponents right here to say that that's g to the j times g to the k. But remember, g to the j and g to the k, that's just phi of j and phi of k, respectively. Therefore, phi of j circle plus k is phi of j times phi of k, and we've shown that phi preserves the operation. Now, the important part of this chain of equations really is in this step right here. And we can see that's true because j ordinary addition with k is some multiple of n plus the circle plus of j plus k. And if you look, you'll see that g to the n is the identity. So when you raise g to these powers, this bit really has no effect. Okay, item B is a similar sort of argument where we define phi from the integers to your infinite cyclic group just by phi of j as x to the j. The next collection of theorems has to do with subgroups. We start with two groups, g and k, and a homomorphism from g to k. So there are 4 parts of the theorem. So if h is any subgroup of g, then the image phi of h is going to be a subgroup of k. Likewise, if j is a subgroup of k, then its pre-image phi inverse of j will be a subgroup of g. The third part says that if j is a normal subgroup of k, then the inverse image, phi inverse of j, will be a normal subgroup of g. And then finally, if phi is onto and h is a normal subgroup of g, then phi of h will be a normal subgroup of k. Well, we'll prove one part of this theorem. We'll look here at part B. So we're starting with a subgroup j of k. So j lives over here in k, and we're going to consider the inverse image, phi inverse of j, that lives back in g, and we want to show that it is a subgroup of g. So how do we do that? Well, you might recall back when we were talking about subgroups that you can show something as a subgroup by showing that it's closed, meaning that if you take two things in there and multiply them together, you get a third thing that's in there. And also that if you take anything in there, that its inverse also lies in there. So let's start with two elements of phi inverse of j. If we apply phi to both of those elements, then you wind up back in j. J is a subgroup of k, so when I combine them together, I get a third element in j. And then phi is a homomorphism, so this product here can actually be expressed as phi of g1, g2. So phi of g1, g2 lies within j, and then applying, phi inverse, the inverse image, we know that g1, g2 lies in the inverse image of j. Okay, so that's the first part. Further, if you take phi of g1 inverse, that's going to be in j because j is a subgroup. And phi of g1 inverse is phi of g1 with the inverse inside. That's due to one of our previous theorems. And so that means that g1 inverse is in this inverse image of j. So phi inverse of j, it's closed under multiplication and inverses, and therefore it's a subgroup of g from probably, I think, theorem 5.1 back in section 5. We finish our discussion today by talking about Cayley's theorem. This is an important theorem that says that if G is a group, then G is isomorphic to a subgroup of the symmetric group S sub G. So this S sub G is just the collection of bijections from G to itself under the operation of function composition. Now, in terms of finite groups, what this says is that if the order of G is n, then that says that G is isomorphic to a subgroup of the symmetric group Sn. Okay, to prove this theorem, we start by identifying some special members of the symmetric group S sub G. So remember, these elements of the symmetric group are functions, in fact, bijections from G to itself. So we start with little g in capital G, and we're going to define a function, f, from capital G to itself, that takes any element x and multiplies it on the left by this fixed element, little g. So it turns out that this function is a bijection and therefore a member of the symmetric group S sub capital G. Now, we're going to define a function phi that goes from our group G into the symmetric group by having this function send little g to the corresponding function f sub little g. So what we want to do to finish the proof of the theorem is to show that this phi is a monomorphism. So what that means, monomorphism, that means that phi first is a homomorphism, meaning that it preserves the operation, and that phi is 1-to-1. So monomorphism means two things. It means homomorphism plus 1-to-1. So the first thing we'll do is handle the 1-to-1 business. So suppose you have two elements in the group and phi of G is equal to phi of H. That means that these associated functions, f sub G and f sub H, are equal. And that means that when you apply them to the identity, the results must be equal. But remember, f sub g of anything just multiplies by g on the left, and the same thing with f sub h. It multiplies by h on the left. So we get g times z equals h times z, and that means that g equals h. So we started with phi of g equaling phi of h, and we ended with g equaling h, and therefore the function is 1-to-1. Now we need to show that phi is a homomorphism. So we start with two elements, g and h, in capital G. And now if you take some arbitrary element x in G, so phi of the product g times h, that is a function that takes capital G to itself, and so we can apply it to an element x in capital G. So phi of g times h, that's f sub gh applied to x, which has the effect of multiplying x on the left by gh. But by associativity, that's the same as g times hx, which is g times f sub h of x. But multiplying by g on the left is the same as applying the function f sub g. And then that's applied to f sub h of x. So this is a composition of functions right here. So that's f sub g, circle f sub h of x. But remember, this is the operation over in s sub g. Remember, the operation on this collection of functions is function composition. So we've shown that phi of a product over in capital G is the product of the individual images over in S sub G. And that's what we needed to do to show that phi is a homomorphism.